Okay, so in the last video, we really defined what a partition function was in kind of this generic energy term. And then we started talking about that we could define this partition function based upon the energies found within a molecule or the big E, the total energy of the system. And so now we're going to think a little bit more about how this molecular energy and the partition function relate to each other. So now, one form of energy that molecules have is vibrational energy. And when we think about vibrations, we think about the these are known as normal modes of vibrations that can exist. And when we do what's called a normal mode analysis that we're not going to go over, you might cover it a little bit in quantum mechanics and PChem 2, but if you are really interested, that means that you're a spectroscopist and you should take graduate level quantum mechanics where you really get into normal modes. So diatomic molecules, the only normal mode that they have are stretches. We've got two atoms attached by a spring or a bond, and all they can do is stretch. There's nothing in the middle to allow them to bend. If we have a nonlinear triatomic, we can have, which means that we have three atoms hooked together. So this is something like water. In this, we can stretch in a couple of different ways, where it's a symmetric stretch, where these bonds are stretching outwards at the same time, or an asymmetric stretch, where one is going in and the other is going out. We can also bend, where this angle between the atoms is changing. And then with linear triatomics, we can also have stretching and bending vibrations, but the modes are a little bit different. We can have a symmetric stretch where the bonds pull in a symmetrical way. We can have an asymmetric stretch where one bond stretches and the other bond compresses. We can have what we call an in-plane bending, which means that this molecule folds. Or we can have an out-of-plane bending, where the molecule folds, but in the z direction. That's what these arrows, this is coming at you. That's how we indicate our three dimensions. Okay, so let's get this into perspective. We've really got to make sure that we're understanding the potential molecular energies that any molecule in a sample could have in perspective with the temperature. Most of the energy under normal conditions is in the form of rotational and translational energies. So that means that we are in our ground state for both our electronic and our vibrational energy, and then we can have population of higher rotational levels. And remember that translational energy isn't quantized, and so that means that translational energy is something that all molecules have. But notice how the gap between the V equals 0 and the V equals 1 energy level and vibrations is not nearly as large as the electronic gap. This means that sometimes vibrational energy really can contribute, especially if we start changing things like the temperature. And so, therefore, we really work to make sure that we understand how to be able to calculate the populations of this vibrational contribution. So, way back when, I had you watch a video all about the different types of energy within a molecule, and then we kind of ignored it. Well, guess what? It's coming back. So, when we are considering the vibrational energy of the molecules, we can replace this generic energy of a partition function. Remember that we had our P of epsilon is equal to G of epsilon times e to the minus epsilon I over kBt, all divided by our Q of T. Well, we are going to work to really be able to replace what this is. And remember that this Q is equal to our sum of overall space of this e to the minus ei over kBt. So if we define ei for the numerator, we also are going to have to define it for the denominator and figure out what Q of t is for the energy case that we're looking at. So way back when we defined vibrational energy, we found that the energy of a vibration is equal to V plus a half times omega E. And we're going to work to understand what this is. But really, we're going to talk a lot more about this. But to start you off, we have these different vibrational energy levels with these are vibrational quantum numbers. And given the vibrational quantum number, we can calculate the energy of that level within reasonable approximations. So the V equals 0 level is found at the energy that we give 1/2 omega E. And then if we start thinking about the transitions between these, that there's a transitional energy of omega E, which basically is the gap between these. Okay, so let's break this down. For the vibrational partition function, the numerator, this G of epsilon equals e to the minus epsilon over kBt. G of E, let's talk about this degeneracy. For vibrational modes, there is a way to calculate degeneracy. We are not going to do it. It involves a lot more knowledge of quantum mechanics and vibrational spectroscopy than we are going to go into. And so for you guys, the degeneracy of vibrational modes will be given to you in the problems. But to give you an idea of what we're talking about with degeneracy is that degeneracy are going to be identical vibrations that have the same energy. So what do I mean? Well, if we look at the cisplatin molecule, this 4-chlorine, I don't know if this is cisplatin. I don't know if it is or not. This is platinum Cl4. In this, there are 2 doubly degenerate normal modes. And so the one that is being indicated are the 2 bottom chlorines going in and the 2 upper chlorines going out. Well, there is another motion where the upper chlorines go in and the bottom chlorines stretch out. Those 2 modes are different because they involve different atoms, but they're going to have the same energy because the atoms involved in what's called the symmetry of things are identical. So likewise, this bending motion there's an opposite yet equal motion where the bottom chlorines go in and the upper chlorines go out. And so this degeneracy indicates that there are two possible modes for both of these motions. The key with degeneracy is that things have the same energy. So now, to figure out the energy of the vibrational level, we remember that we said that E of V is 1/2, backwards, but backwards, but the same. V plus 1/2 times omega E. Well, this half is going to make our lives complicated. So what we are going to do is we're going to make an approximation that this half really doesn't matter. And so we're going to say that EV is approximately equal to omega V times omega E. And so what we can do is we can plug this expression in where that energy existed and have a more specific term that is dependent upon this vibrational energy. And so how can we make this approximation that this 1/2 doesn't matter? Well, it turns out that the bottom of the vibrational energy never exists. The first vibrational energy state is this V equals 0, and it's not equal to the electronic energy. So this point is the electronic energy. This is our 1/2 omega E, and this is what's known as the 0 point energy. And so what we are going to do is we're basically defining that this is equal to 0. And so that allows us to shift everything by that 1/2 omega E, making our lives a bit easier. Because if I subtract 1/2 omega E from this, I get 2/2 omega E, or just omega E, which with V equals 1 is what we have. I subtract 1/2 from here, I have 4/2 omega E, or 2 omega E, and V is 2. And so really we're just shifting where our 0 is, because this bottom of this energy well for vibrational energy is never filled. Wait, let's go back. So now we have the numerator. So G of E is our degeneracy. We said this is given. And this is our vibrational energy. Well, now we have to figure out our denominator. Okay. So in our denominator, our Q of T is now this expression. All I have done is I have replaced the epsilon I with the our approximation of our energy, our vibrational energy level of the vibrational energy state times the this omega E term that we haven't quite explained yet, but I'll get to it. So we have this infinite series going on, and I don't know about you, but sequences of series did not go the best. And so we're going to skip that part of the math because it doesn't really matter for us. We just need to know what the end result is. And so we make some very reasonable approximations, and we use a Taylor series expansion. And this allows us to create an expression for the vibrational partition function, which is given by this term. So this is the vibrational partition function. Remember from this, I missed that fraction. So remember that this P of V gives us the fraction, and so we put our state, our individual state, with our individual V on the top, divided by our Q. And you will see that I made a mistake in my formula. I will change this in the slides because this bottom is 1 over that. This one should be a fraction, so it should be P of V is equal to E to the minus V omega E divided by KBT, all divided by 1 over 1 minus E to the minus omega E divided by KBT. So the vibrational partition function really tells us this fraction of the molecules in a given state. And in this case, we're thinking about that given vibrational level. So let's take a moment. What is this omega E? This omega E, this is the fundamental vibrational frequency of a mode. So this omega E, this is really what you were looking at in infrared spectroscopy. So if we said that a stretching vibration was at 1500 wave numbers, so that means that if we think about this energy well, that the difference between these two energy, between V equals 0 and V equals 1, is 1500 wave numbers, or omega E. Sorry, I will make that neater so that you can actually read it. Okay, so that energy separation allows us to get the fraction of molecules in the different states with our math of our partition function. Okay, so I've been using this wave numbers thing. It is a convenient energy unit. Really, so spectroscopists mostly, but also a lot of physical chemists, were odd and probably a little lazy. So we then, because of this, we choose a very convenient but strange unit to express energy. Wave numbers, given as centimeters to the minus 1, is a unit that is proportional to energy. And it's really kind of a frequency, sort of. Because if we multiply wave numbers by the speed of light in centimeters per second and Planck's constant, it gives us the energy of a vibrational mode in joules. So you should convince yourself that if you take this times 1 over wave numbers, that you are going to get energy with units of joules. So you'll hear me say that wave numbers are energy. That is because I'm a spectroscopist, and as far as I'm concerned, HC's a constant, and therefore we can just scale everything by that amount, and we can treat wave numbers as energy. Okay, so you're now try this, is to find the fraction of molecules, sometimes we call this the abundance or the population, of the ground vibrational state of iodine chloride. So this is ICl. Strange molecule. But we're working at 298 K. The vibrational constant is 384 wave numbers, and the Boltzmann constant is given as this 0.695. Okay, so stay tuned. The next video, we're going to work through rotational partition functions, and then we'll work on translational.